Prabhanjan and Ananth. I'm fully homomorphic NIZK and NIWIs.
Thanks, Ron. Can everyone hear me? Okay, cool. So I'm going to talk about fully homomorphic NIZK and NIWI proofs. And this is in joint work with Apurva, Yael, who's here, and Anna. So due to current advancements in technology, many a times the traditional crypto primitives are no longer sufficient to meet the current security demands, right? And one way to overcome this problem is to augment the known crypto primitives with additional properties. And one such property considered in the crypto literature is homomorphism. And homomorphism is best explained using the notion of fully homomorphic encryption. This remarkable notion allows you to combine many ciphertexts into a resulting ciphertext of a message that is a function of the original messages. Okay? So this was a remarkable notion and has tremendous applications in cryptography. And homomorphism was not just studied in the context of encryption. There have been other primitives as well. For instance, homomorphism has been studied in the context of signatures. It has also been studied in the context of secret sharing. And the list goes on. So this workshop is about proofs, right? So a natural question to ask is, can you combine homomorphism and proof systems? And in order for this combination to even make sense, we are going to focus on non-interactive proof systems. So before I formally define what this means, let's just look at an intuitive definition of fully homomorphic proofs. So intuitively, what we want is we should be able to combine many proofs on many instances into a proof on some instance that is a function on the original instances. And the two natural properties we want is that if you start with proofs on yes instances, and suppose let's say these are proofs that are accepted by the verifier, and suppose let's say the resulting instance is also yes instance, then you want the guarantee that this proof is also accepted by the verifier. Okay? So this is the correctness guarantee. And the soundness guarantee says that it doesn't matter what proofs you start with. Maybe these instances are yes instances, right? If you result in a no instance, then the proof should be rejected by the verifier. So I'm going to formalize what this means in a second. So as you have seen in this workshop, just correctness and soundness in a proof system alone doesn't suffice. There are two directions we can take. Either we can take the succinctness direction or the privacy direction. Succinctness here talks about the proof length being much smaller than the witness size, right? And privacy somehow guarantees that the proof hides the witness. What hides means can be formalized in many ways. And in this work, we are going to take this privacy direction. Okay? We are going to propose two notions of fully homomorphic NIZK and NIWI proofs, and we are going to give constructions for both these notions. So why is this notion? Yeah?
You don't mind if the eventual proof is as long as all the...
Yeah, it will be long, yeah.
We mind, but that's all good.
Okay, so why study this notion? Oh. My wife works in a consulting firm, and her day-to-day job is to collect medical data from different research groups. And these research groups, in turn, generate this medical data from many sources, right? And their job is to come up with a model that sort of fits this medical data, and then they sell this model to clients, for instance, pharmaceutical companies. Now, there are incentives for different entities in this system to lie. Maybe the consulting firm promised the pharmaceutical company that they're going to deliver some model in some period of time, and then later realize that they couldn't do it. Maybe they now generate a fake model to convince the pharmaceutical company, because they don't want to lose their reputation. So in this case, we want to impose a system where these entities don't lie. And one way to do this is to make these different entities prove whatever they're doing. Right? So for every outcome, they need to publish a proof that they have followed certain procedures. And here itself, we can see that you need some form of homomorphic proofs, right? Because these consulting firms just don't talk to one research group. They talk to many groups, so they receive many proofs. So somehow they should be able to combine these different proofs together to publish one proof. And you also want some privacy guarantees because you don't want the proof given by the consulting firm to this company to not reveal information about how this model was generated. So now let's look at what it means for a proof system to be fully homomorphic and satisfy zero knowledge property. So in order to define the proof system, first I need to define the relation. Okay, and the relation we are going to consider is this relation where every instance in this relation consists of two parts. The first part is a circuit and the second part is a bit. And a witness W belongs to this relation if the output of the circuit on this witness is this bit B. Okay. And as you can see that this captures NP-complete languages. Right? And the reason why we consider this relation is because this has some natural composability property. If you combine many instances in the language corresponding to this relation, then you will end up with an instance that also belongs to the language. For instance, in this example, suppose let's say you have C1, B1 through C and Bn, and suppose let's say you want to compose them using some circuit C. One way to do it is just to augment this circuit C on top of all these circuits, right? And so now the witness for the final instance is just a concatenation of the original witnesses. Okay, is this clear? Okay, so what are the algorithms associated with this proof system? As in a zero-knowledge proof system, you have the setup algorithm that outputs a common reference string. And there's a proof algorithm that outputs a proof for some instance. And the eval algorithm, which is different from the existing proof systems, takes as input a CRS. It also takes as input the circuit that you're using to compose. In addition, you will take as input different proofs on different instances. And then this eval algorithm outputs a proof on the homomorphically evaluated instance. Okay? And C star is obtained by composing C with the circuits C1 through Cn. And finally, you have the verification algorithm. Okay, so let me describe how these algorithms are evaluated. Yeah.
What is the right? So the verifier algorithm only gets C and the final output B.
Yeah. I mean, this is an instance. Yeah. Okay, so I'm just going to pictorially denote how these algorithms work. So now we have the setup algorithm that generates a common reference string. And this common reference string is given to different parties who generate proofs on many instances, right? And then there is a public homomorphic evaluation algorithm that takes as input these different proofs on different instances, gets the final proof, and then the verification algorithm outputs accept origin. Okay, so again, what are the properties we need? It's the same as before, right? So we want that as long as the original proofs were acceptable by the verifier, then you want the new proof should also be accepted by the verifier. And similarly, we want the property that if an instance is a no instance, then they should be rejected by the. Sorry, there should be another bit B here. It's a typo.
So the composition only takes all proof. You don't have new witnesses or something.
No. Yeah.
I have a question.
Yeah.
Is it possible that each of the individuals xi are yeses, but the combination is not, or is it?
So in this case, that won't happen. If you're combining yes instances, you will always end up with yes instance. Okay, so what about privacy guarantee? So the intuitive privacy guarantee we want is that if the original proofs are zero knowledge proofs, then the resulting evaluated proof should also be a zero knowledge proof. And we are going to satisfy this by defining this notion of unlinkability. Okay? So what does unlinkability say? This unlinkability says that if I generate a fresh proof on the instance C star, comma, C of B1 through Bn, right, using the witnesses W1 through Wn, this should be indistinguishable from a homomorphically evaluated proof on the same instance. Okay. So, and this notion is inspired by the notion of randomizable proof systems. Yeah.
So earlier you mentioned that as we go through these evaluations, the proof might grow.
Yeah.
And how does it square this unlinkability that maybe a fresh proof might be shorter than like?
No, it won't be. So in our case, the fresh proof will also grow with the instance size. I mean, once you evaluate the proof, it will just grow with the instance size.
So in particular, the structure of the circuit is not being hidden, right?
Yeah.
And the circuit just keeps growing.
Yeah, exactly. Right, because this circuit is also a big circuit. It's obtained by. Yeah.
So wait, this is a security property on top of like the naive thing that you would want, or is this like part of your basic?
Good. I'm going to get back to that in a second. Yeah.
So let's say the initial circuits were some kind of universal circuit because the structure, as Amit pointed, is not hidden.
Yeah.
So then this bigger C star is a bigger universal circuit because it incorporates all of them. So what will be the structure of the bigger circuit? It's like bunch of universal circuits put together? Or?
So it will be a bunch of circuits. On top of it, another circuit that you're composing. Right. So if I go back. Yeah. So this is how it will look like.
Oh, so C12, like the C's and the C12, Cn will all be leaked.
Yeah. Okay. So, right. So yeah. So I'm just denoting this pictorially. So whether you evaluate this using the underlying proofs or you generate the proof afresh, you should not be able to distinguish. So why is unlinkability useful? Coming back to Alex's question. So if you combine unlinkability with the standard notion of zero knowledge, then you get this ideal privacy guarantee that we stated earlier. And the proof is really simple. Using unlinkability, you can switch the evaluated proof to the fresh proof, right? And now, what does zero knowledge say? It says that the proof is zero knowledge, so you can switch the fresh proof to simulated proof. Yeah.
Take the variant, this what Ali was talking about, the variant recursive combination.
So this doesn't satisfy succinctness, by the way. This doesn't satisfy succinctness. Yeah.
Right, it doesn't. But then also it's unlinkable, right? But you don't know anything about the original proofs.
So I don't want to comment on their construction because it's in a different setting. Yeah. But in order to guarantee unlinkability, it's not just about composition. You also need to re-randomize because you want to hide the fact that you actually composed, right?
Okay.
Does that make sense?
But also they need a snarks.
Yeah. It's a different, yeah.
They need snarks, which is a very strong notion. Talking about.
Well, but never mind. I'm saying it sounds like it should be a special case completely, but it's not. So there's some other issue.
Anyway, we can talk offline. Okay, another interesting, yeah.
If you start with like zero knowledge proofs, then you have unlinkability. You get zero knowledge for the couple string.
Yeah.
But you could just like forget about unlinkability and just require zero knowledge for everything, right?
That definition becomes a little clumsy. So what you're essentially saying is that you need to come up with a simulator that takes as input simulated proofs and output another simulated proof. That is indistinguishable.
They just want like the homomorphic proof doesn't reveal more information.
So this unlinkability is useful much more than getting zero noise for the evaluated proof, as I'm going to talk about now. Right? Yeah. So for instance, if you combine unlinkability with single hop evaluation, you also get multi-hop evaluation. Okay. So and the proof is also very simple. So suppose let's say you do have a proof that you obtain by composing, evaluating many proofs, right? And now this proof looks like a fresh proof by unlinkability property. So now you can combine it with more other fresh proofs and get, again, homomorphically evaluate these proofs to get another evaluated proof and so on. So you can keep on recursively doing this. Yeah.
So just a question about why a naive thing wouldn't work. So
sorry, what?
Question about why a naive thing wouldn't work.
Okay.
So I have my proofs, like K proofs. I forgot the parameter. If I treat them as like no empty witnesses and just run a fresh proof system on the.
Then the size keeps growing.
But that's what you get.
I mean, you do still want that it's polynomial in the instance size, right? Like what you're suggesting, it will grow very fast.
So what is the restriction?
One hop will.
I should be able to do this how many ever times I want, right? Like any polynomial. Yeah.
Number of times. Yeah. So the overhead per time should get a constant or something.
Yeah. In this case, and also it won't satisfy the unlinkability definition as well. Yeah. What you're suggesting?
size.
You would think that it could. You could pad it to like the maximum like proof size of a circuit of the size that you're talking about, right? I mean,
yeah, but
the question of blow up, I think, right? If you could do this thing and blow up like additively and not
Right.
duplicatively or something, then you'd be in good.
yeah, you can do that, but in our case, you don't even have any blow up. Like we can achieve.
Even additive is a problem.
You can't even have one bit
Yeah.
blow up, because then you'll have 1, 1, 1 eventually.
Okay,
it'll be-
well, I'm allowed to grow with the circuit size, right? With every gate, you can think about it as a gate by gate thing. If for
No,
every
but-
gate I pay a penalty of 1 additional bit, then I can
No,
sort
but
of
the
set
question
my
is, you
size
pay
so that.
additional bit beyond what will look like fresh.
No, I can set the fresh thing to be the.
But that will only again, whatever is suggesting will only go till some bounded number of evaluations, right? That's it. Like so, in my case, I can go to any unbounded number of evaluations. So in your case, you need to fix a priori the bound, and then the parameters will grow with the bound. In my case, it's not the yeah. Okay, so these are the properties we need. I mean, complete correctness, soundness, and zero knowledge and unlinkability. So you need zero knowledge in addition to unlinkability for us to get privacy. Okay, so the definition of homomorphic NIWI proofs is identical, except that there won't be any setup. No, we just have the algorithms prove, eval, and verify. And in terms of completeness, soundness, and unlinkability definitions, it's the same as before. Now you additionally also have the witness indistinguishability guarantee, which just says that if you compute the proof with respect to one witness or with respect to a different witness for the same instance, you should not be able to tell apart. Okay, so let me state our results.
But you still require the unlinkability to be, it's not the WI property.
So the unlinkability says that if you, unlinkability just says that it should be indistinguishable from a fresh proof. So now if you combine it with WI, you get like, yeah. Okay, so we show that there exists fully homomorphic NIZKS for NP in the common random string model. We get our results in the common random string model based on decision linear assumption in bilinear maps. Okay. So what is this assumption? I mean, this assumption has been fairly studied in the bilinear maps community. It's a symmetric group, so you define a bilinear map on the same group, and then you have a different target group. You know, suppose let's say you want the order of both the groups to be the same prime P, right? And then the assumption states the following. So suppose let's say I give you the generator of the group, and I give you g to the x, g to the y, g to the xa, g to the yp. Then you should not be able to, given this information, you should not be able to tell apart g to the a plus b versus g to the r, where r is picked afresh, independent of all other values. Okay, it's clear? So we also show how to get fully homomorphic NIWIs for NP in the plane model. As I said earlier, there's no setup based on some falsifiable assumption on bilinear maps. I won't be describing this assumption, but let me just give you a flavor of how this assumption looks like. So it will essentially be DLIN with some auxiliary information. Okay? And this auxiliary information will be some constant number of group elements whose exponents would depend on these values, x, y, a, b, and r. Sorry, x, y, a, and b.
Are you going to say anything about why DLIN doesn't suffice here as compared to in the NIZK case? Or?
We don't know the answer to that question.
No, but like within your proof, like why?
Oh, that I can explain. Once I give the overview, I'll explain. Yeah. Okay. So in terms of related works, related works have mostly focused on the case when you're only homomorphically evaluating a single instance and proof pair. Right. And moreover, even in this regime is called malleable proof systems. Even in this regime, they have either focused on restricted class of relations, in which case they show how to get such proof systems from bilinear maps, or they can actually get it for general relations from knowledge assumptions. Or you can even get general relations, but homomorphism with secret state, meaning that the evaluator has to have some secret information associated with the original proofs. Even this we can do. So for the homomorphism case itself, where you're homomorphically evaluating multiple instances, we know very restricted class of, we know results only for restricted class of relations. You have a question? Yeah.
So suppose that I care about C just being the conjunction, so I want all the x's are in the language. That's what I care about.
Yeah.
So isn't what you're saying achieving some notion of compactness? I mean, I have these like proofs for each one of the xi's.
Yeah.
Now, to check that all of them are in the language, it sounds like the proof length will be as long as like one of them.
No, it will be proportional to all of them, a sum of all of them, sizes of all of them.
Say the length for a single instance is m. I want to check that all a single witness is m.
Yeah.
Yeah. And I want to check that all k of them are accepting. You're saying the new proof will be like k.
Yeah, it will grow with the instance size. In our case, it will grow with the circuit size.
So how does it work with multi-hop then?
I mean, multi-hop, the instance size also grows. So correspondingly, yeah. So once you evaluate, you're not getting rid of the original circuits. I mean, you're going to keep this.
Circuit building up.
So as some of your questions have alluded to, there have been like a lot of works in terms of homomorphically evaluating succinct proofs under the umbrella of incremental proof systems. This was first proposed by Valiant. And what does our work say about succinctness? Nothing. So we don't achieve succinctness. But even achieving privacy alone seems very challenging. So, and in general, there are techniques to generically combine NIZK proofs and succinct proofs in order to get the best of both worlds. And we hope that our work will be a starting point in this direction.
Okay. So just to make sure about the previous discussion.
Yeah.
So it could be that those things, the valiant thing, there could be a thing which is a valiant thing and is also satisfies your notion, right? If the original one is
again the assumptions we want. Okay. Yeah.
Even the original one was succinct, so
yeah.
The independent one, so we just create another independent, re-randomized independent process.
It's possible. If you don't care about assumptions, then it is possible. Yeah.
Just about the notion.
Okay. So let's dive into the construction. How much time do I have?
One technical comment there. Since the unlinkability property says that you don't know whether you are composed or not.
Yeah.
And say in Valiant's case, like kind of knowing how deep you are is pretty important because you know when to stop your extractor when you go back. If you didn't know whether you're fresh or not, then you kind of don't know how much to extract into the past. I don't know how to.
But this is also the case when you generate a fresh proof, right?
5 minutes, okay. Okay, so we can take the discussion offline. Okay, so let me give an overview of our construction. So the starting point to our construction is the NIZK construction based on DLIN by Jens, Rafi, and Amit. So I'm going to stick with the same relation as before. So let me just briefly describe how their proof system looks like. So the goal is to prove that some instance CB belongs to the language. So the circuit looks, suppose let's say the circuit looks like this, and then you have a witness here, and there's a bit that's the output of the circuit on this witness. So the first step is to evaluate this circuit. So you have these intermediate values. So the next step is to commit to the intermediate values as well as the witness, okay? And you also commit to the output wire. Okay? And the parameters associated with the commitment scheme, I'm going to use the word parameters a lot from now on. These parameters will be in the CRS. So, and moreover, note that the commitment for the final output wire is computed using randomness 0. This is to enable the verifier to check if the output was 0 or 1. Okay. So the next step is to show that these values are indeed 0 or 1. And finally, they show proofs of consistencies. You want to make sure that the values committed here are consistent. That is, W5 is obtained by NAND of W1 and W2, for instance. Okay. So you have 3 consistency proofs. Okay. So I'm going to call the proofs where you prove that the committed values are 0, 1 as the bit proofs, and the proofs that prove the consistency of the committed values as gate proofs. So natural question to ask is, can their proofs be made fully homomorphic NIZK proofs? And the way you would do it is to add a homomorphic evaluation algorithm. A natural way to add homomorphic evaluation algorithm is, suppose let's say you have two instances, right? So you have these commitments, right? So suppose let's say you want to join them with some NAND gate, right? So what you do is you evaluate NAND of B1, B2, and then you commit to it using the same parameters. Right? Okay. Of course, and then you also need to compute a gate proof, right? Of course, this is not secure because remember I said that these commitments are actually commitments with respect to randomness 0, right? So you no longer can afford to leak information about these values because they are now intermediate wires. So what you do is you re-randomize these commitments. And re-randomizing these commitments have other challenges because you also need to model the proofs associated with these commitments and so on. So our technical contribution here is to show how to carry out this approach. We want to re-randomize the commitments and show how to modify the proofs accordingly. Okay? So this was a simple modification of the Kreutzkopf-Ostrowski-Sahay construction. So the next step is going to be more challenging, which is to construct fully homomorphic NIWI proofs. And to do that, let me just briefly recall how the NIWI proof system looks like. Okay? So the NIWI proof system is a modification of the NIZK proof system, where now note that there's no parameter in the CRS anymore, right? So there's no CRS. So the prover has to generate the parameters, right? So we're going to make him generate two parameters. And what is the point of making him generate two parameters? They have these two very nice properties that one of these two parameters has to be binding and the other has to be hiding. Okay? Oh, sorry, one of these parameters has to be binding. The other will correspondingly be hiding. And moreover, the binding and hiding parameters will be indistinguishable. Okay. And roughly, we are going to use hiding to ensure witness indistinguishability and binding to ensure soundness. Okay, so the proof structure is almost the same as before, except that instead of generating just one commitment per wire, we're going to generate two commitments. Okay? And these two commitments will be with respect to these two parameters. Okay? And you still prove consistency for all three commitments. This green commitment will be with respect to green proof will be with respect to green commitments, and the blue proof will be with respect to the blue commitments. Okay. So I'm going to skip the WI proof, their proof. So a natural question to ask is if you can extend again NIWI proofs to FH-NIWI proofs, right? And this step turns out to be very challenging. Okay? And the reason is because there's one prover who computes this proof with respect to his own pair of parameters, right? And there's another prover who computes another proof on a different instance with respect to his own pair of parameters. So now, how do you join these two proofs together? Because they are computed with respect to these different parameters. Okay? So that's the first issue. You somehow have to make sure that these commitments computed with respect to different parameters interact with each other. And the second issue is unlinkability. If a fresh proof were to be constructed, then the prover is only going to use two parameters for the whole proof, right? But if you join both these proofs together, then you'll be left with 4 parameters instead of just 2, right? Note that this problem didn't exist in the NIZK construction because there's only one parameter and that was in the CRS. Okay, so the new idea is to actually have 2 parameters for every gate in the circuit. So we're going to have binding hiding parameter for every gate in the circuit. And then we are going to make the prover commit to the bit value with respect to both these parameters. So suppose let's say during the evaluation of the circuit, the wire value was B1, and then you're going to commit with respect to PP1 and PP2 here. And similarly here, if the output of the NAND gate was B2, you're going to make him commit to PP3, commit to this value using both PP3 and PP4. Okay? but now how do these commitments interact with these parameters, associated with this gate? Because these wires do go into this gate, so somehow we have to make them compatible. And one way to make them compatible is just to make the prover also commit to B1 using these two parameters, right, associated with this gate. Yeah. So now with respect to every wire, you're left with 4 commitments, right? Yeah. This obviously leads to one important challenge, which is that how do you ensure that whatever commitments the adversarial prover has given contains the same value? For all you know, he could be cheating here, right? So this is going to be the technical contribution of this construction. So what we show is we somehow show how to have 4 commitments, and we're going to have 4 proofs between all these commitments in such a way that proves consistency across the commitments between any pair of indices. Okay. And the reason why we do this is that this automatically gives us soundness, because one of the pair of parameters has to be binding. Recall that this was the property guaranteed by the GOS scheme. Here also one of the parameters has to be binding, right? In which case there has to be some line, in which case both the vertices on this line have to correspond to binding parameters, right? Which will ensure that the value committed to along that line is the same. So this will automatically guarantee soundness. The witness indistinguishability is going to be tricky because if you go back to GOS proof, the way they prove witness indistinguishability is arguing for hiding and binding parameters separately. But the problem here is that these proofs are going to be intertwined, so it's unclear how would you switch from one witness to another witness here. Okay? So I'm not going to have time to describe the details of this construction. So if you're interested, I can talk to you offline.
Yeah. By the way, for these proofs, you're going to, since they're also sort of perhaps going to be NIWI proofs,
yeah,
you're also going to sample fresh CRS is sort of going to be non-black box in the underlying proof. Like it's going to take the verification algorithm and the commitment, unroll it as a circuit, and do it.
So there is no NIWI, there is no CRS here, but
no, I mean like the underlying CRS, like P5, P6. I'm thinking of that the CRS of the underlying proofs.
Yeah.
Verification. So the pi1, pi16, pi5, pi26.
Yeah.
Those proofs are going to be non-black box in the verification algorithm of the underlying pairing algorithm. Is that correct?
Don't quite understand your question, but I can talk to you offline about it. Yeah. Okay. So let me conclude. So we defined fully homomorphic proofs. We showed how to construct fully homomorphic NIZKS and NIWIs from assumptions on bilinear maps. For the FH-NIZK construction, we give a new way of randomizing and modeling proof systems, GOS proof systems. And finally, we show how to, we give a new proof technique that proves that different commitments computed with respect to different parameters have the same value. And there are some obvious open problems, basing FH-NIWIs on known assumptions. Recall that our assumption was some variant of DLIN and not DLIN. Second is lattice-based FH-NIZKS. We have lattice-based NIZKS now, so can you actually get homomorphism as well? And another question is to combine succinctness and fully homomorphic NIZKS. And finally, are there other applications of homomorphic NIZKS?
And that's it.